Now I want to talk about the correlation coefficient. We, in our last example, created a line that represented the data points that we had for Denver. However, we also want to know if a linear model, if using a line to go through the data, is actually the best fit, or if there might be something else that would be a better model. So right now we're focusing on, is it a linear model, or could something else actually be better? All right, so a correlation coefficient is a number, and that number is going to range from -1 to 1, and that represents the measure of the strength and direction of the correlation of our x's and y's. So if we have a number that's close to -1, that's considered a strong negative correlation. And what's close, we're going to say that an R value that's less than or equal to -0.7 is a strong negative correlation. As we move along our line here, if we get to a number where R is very close to 0, that means it's no correlation at all. It looks like a true scatter plot, like somebody just threw darts at a dartboard and plays about as well as me. No correlation if we're somewhere close to 0. And then as we move along towards a positive correlation and we get closer and closer to 1, let's say greater than or equal to about 0.7, then we would consider that a strong positive correlation. So you can see some examples down here where we definitely have a strong negative correlation. Notice that all of those points are very, very close to our line. We've got an R value that's going to be less than -0.7, negative because it's going in the negative direction, a negative slope, and again, we would call that a strong negative. And then our second one would be an example of not much correlation at all. You could maybe say that there's a weak positive correlation, but I'm not even sure you could do that. And then finally, if we have an R greater than or equal to 0.7, and you can see that that line is very close to all of the points, then we say that we have a strong positive. So looking at the top of the next page, let's just summarize that and say that the closer that value is of R to 1 or -1, the stronger our correlation, and the closer it is to 0, the weaker our correlation. So we're going to want to identify our correlations as weak or strong. Remember that if it's a strong correlation, that means that a line is probably the best model for the data. If it's a weak correlation, we would need to investigate further and see if there was another type of function that might fit the data better. All right, so we're going to use our linear regression model. You can do this on a graphing calculator. Our graphing calculator of choice is going to be Desmos for this because you all have access to it. And we want to figure out the equation, a linear equation for the data in our example. And then also we want to figure out what the correlation coefficient is and decide what that means in terms of strength and direction. Is it strong or weak, positive or negative? So we have data points on a scatter plot. I want to convert those to a table of XY values so that it's easy to put into Desmos. So I have a value at 1 and 5. I'm going to mark that one as used. 2 and 2. 3 and 1. 5 and 2. And then also 5 and 5. Notice that I'm marking those off on my graph as I do them to make sure that I catch every point. So I have 5 points there. I have 5 points on my data table. I'm good to go. So let's go ahead and go over to Desmos and see what this tells us. All right, so I've put the data table into my graph and I've kind of adjusted my graph to be able to see the data all at once. Can do that. And then if I try to plot a line through this, well, gosh, we aren't anywhere close to any of our data points. You can see that the line is going slightly negative, so we know it's a negative correlation. But notice what the R value, the correlation coefficient is. It's negative 0.07. That is a very, very weak, close to 0. It's not 0.7, 0.07. So that's a very, very weak, but we can tell that it's negative because it does have a negative in front of it. I have my parameters for m and b as well that we can use to write our equation, even though we know that a line is probably not the best data fit for this particular set of data. All right, so our equation, grabbing the m and the b from our Desmos information, was negative 0.08x plus 3.25. And then our correlation coefficient was that very small number of negative 0.07, meaning that we are negative because we have a negative there, but it's a very weak negative. Let's look at one more example. We can kind of tell just by looking at this data that it's going to be a negative correlation, and probably a pretty strong one. That data looks to be almost perfectly aligned. But let's go ahead and create our XY table. And I'm going to, again, plot and mark things off as I do. 0, 25, 1 and 20, 2 and 15, 3, and I'm going to call that maybe about 9. It looks like it's a little below 10. You'd get a slightly different answer if you said 10, but I'm going to go with 9. And then 4 and 5. So let's take this over to Desmos and see what our equation and our correlation coefficient are going to be. All right, so again, I've put in my data. Just a reminder that we go to the plus and the table button in order to do that. And then I want to see what my equation is going to be. So let's turn that on, and wow, you can see that the data fits this line very, very well. We can see that we have a correlation coefficient R of negative 0.9987. That is super close to 1. And so this is definitely a strong model, and negative because the slope is negative. Notice our slope and our intercept, negative 5.1 and 25. So we can write our equation using those numbers, and we can say that y is equal to negative 5.1x plus 25. So we intersect right around 25. Our correlation was that really big, close to negative 1 number of 0.9987. And so we have a very strong relationship here, a strong negative.